It all started with a bizarre hum that refused to fade. Two American physicists stood baffled in their lab, listening to the strange signal captured by their massive horn antenna. They tried everything, cooling the receiver, recalibrating the system, even scrubbing away pigeon droppings. Nothing worked. This mysterious signal was everywhere. They didn't know it yet, but they were about to make a discovery that would change our understanding of the universe forever. To unlock the secrets of this cosmic static, they needed to venture beyond Earth's atmosphere, free from Earth's interference. They required a satellite so advanced it could trace the oldest light in existence, peeling back the veil of time to reveal how the universe started. Thus, the Cosmic Background Explorer was born. Seeking for answers. When Albert Einstein introduced his general theory of relativity in 1915, his equations hinted at an unsettling truth. The universe was not static. It was either expanding or contracting. For centuries, the cosmos had been regarded as an eternal, unchanging presence. Even Einstein himself resisted what his own work suggested, dismissing the idea as impossible. Yet, in the following decades, a new generation of scientists would rise to challenge this ancient belief. The universe, they argued, had a beginning. In 1929, at Mount Wilson Observatory, American astronomer Edwin Hubble peered through the 100-inch Hooker telescope and saw something extraordinary. Galaxies were racing away from us. Their light was stretched and shifted toward the red end of the spectrum, a sign that the fabric of space itself was expanding. Then, in 1931, Belgian physicist Georges Lemaitre proposed an even more daring idea. The universe had emerged from what he called a primeval atom, a dense, fiery state that exploded outward, giving birth to everything we see today. Skepticism ran deep. The steady-state theory, which held that the universe had no beginning and no end, still had its defenders. Among them was English astronomer Fred Hoyle, who stated in a 1948 BBC radio broadcast, quote, "These theories were based on the hypothesis that all the matter in the universe was created in one big bang." Then, in 1964, an accident changed everything. At Bell Labs in New Jersey, physicists Arno Penzias and Robert Wilson struggled to eliminate an annoying signal from the massive horn antenna. No matter how many times they recalibrated their equipment, a persistent, low-level hum remained. It was everywhere, uniform in every direction. They had stumbled upon the afterglow of creation itself, the cosmic microwave background, or CMB, the last traces of the Big Bang, echoing through the cosmos for nearly 14 billion years. However, the available technology didn't allow them to comprehend the full picture painted by this radiation. The COBE mission. Researchers encountered a seemingly insurmountable obstacle: Earth's atmosphere. This layer of gas surrounding the planet was blurring the signals from the early universe, impeding accurate measurements from the ground. To break through this cosmic interference, researchers proposed launching a satellite into space, beyond the reach of atmospheric distortion, where it could gather pure, unfiltered data from the CMB. The idea was promising, and while NASA was invested in other projects at the time, the agency couldn't ignore this research. With a strict budget cap of $300 million, NASA gave the green light to the project, giving way to the Cosmic Background Explorer, also known as COBE. It took scientists over a decade of trial and error to perfect an intricate system of infinitesimally sensitive instruments working in carefully controlled environments. And just as everything was coming together, a disaster put another obstacle into the mission. On January 28, 1986, the Space Shuttle Challenger lifted off from John F. Kennedy Space Center in Florida, carrying 7 astronauts on what should have been a routine mission. 73 seconds later, it exploded into a fireball. COBE was supposed to ride into space aboard the space shuttle, but now, shuttle-based missions were indefinitely grounded. It seemed as if COBE, already years behind schedule, might never leave the ground. With the shuttle program in turmoil, COBE's engineers were forced back to the drawing board. They now faced a massive redesign. The satellite had to be adapted to launch aboard an expendable rocket instead of the shuttle. This meant reworking everything: the structure, the deployment mechanisms, and the delicate instruments inside. The Big Bang Archaeologist. The final version of the Cosmic Background Explorer was a nearly 5,000-pound spacecraft equipped with 3 key instruments built to unlock a different aspect of the universe's early history as COBE orbited 560 miles above planet Earth. The first was the Differential Microwave Radiometer, or DMR, a device that could map temperature variations as small as 0.00003 Kelvin, intended to help find the origins of galaxies. To ensure absolute precision, 2 of its radiometers were kept at an ultra-stable minus 207.67 degrees Fahrenheit, reducing the risk of getting wrong readings. Next was the Diffuse Infrared Background Experiment, also named DERBY. This tool was intended to locate even the faintest whispers of cosmic infrared radiation. By doing this, researchers could look for remnants of the earliest celestial bodies hidden by interstellar dust. To do this, engineers gave DERBY a multi-band infrared radiometer, which it could use to detect light across 10 different infrared wavelengths, ensuring a clean view of the cosmos. Its 1-degree field of view allowed for highly focused and precise measurements, filtering out unnecessary noise and honing in on the most elusive signals. However, perhaps the most crucial of COBE's instruments was the Far Infrared Absolute Spectrophotometer, or FIRS, the ultimate test for the Big Bang Theory. FIRS was created to measure the spectrum of the CMB itself, comparing it to the expected signature of the Big Bang. Using a system that split and recombined light waves, FIRS was able to analyze the infrared radiation of the sky, searching for deviations that could shed light on the universe's evolution. The mission. 25 years after the discovery of the cosmic microwave background, COBE finally took to the skies on November 18, 1989, atop a Delta II rocket launched from Vandenberg Air Force Base. Once in space, COBE engaged in a sun-synchronous polar orbit, meaning that its movements were carefully controlled to ensure solar rays would not interfere with its measurements. To conduct its observations, COBE executed a slow, deliberate rotation, conducting 1 full turn approximately every 6 minutes. This movement allowed all 3 of its instruments to sweep across the cosmos, gathering microwave and infrared radiation from every possible direction. To prevent distortions from atmospheric gases and the energetic impacts of cosmic rays, COBE used precision-engineered momentum wheels to maintain a stable spin. For over 4 years, the satellite transmitted data back to Earth. At Mission Control, scientists went through the information, filtering out interference, refining measurements, and waiting for the moment when the universe's hidden blueprint would finally come into focus. Then, in April 1992, the breakthrough arrived. For the first time in human history, a full sky map of the cosmic microwave background was revealed. COBE had done it. It had given humanity what NASA later referred to as, quote, the first baby picture of the universe. What COBE saw. One of COBE's most significant achievements was its confirmation that the CMB perfectly matched the black body radiation curve predicted by the Big Bang Theory. The data was undeniable. The universe had started as a dense, unimaginably hot state, and we could demonstrate it by looking at the thermal fingerprint it had left behind. But the most astonishing discovery came with COBE's detailed temperature fluctuation map, showcasing an intricate pattern of tiny variations in the CMB, barely 1 part in 100,000 in scale. Actually, these seemingly minor bumps were the start of the cosmos itself. They were the first signs of density variations in the early universe, which under the force of gravity evolved into the galaxies, stars, and clusters that make up the night sky we see today. Yet COBE's mission wasn't just about taking a look into the universe's distant past. Using its infrared sensing capabilities, the satellite uncovered 10 previously undetected galaxies hidden from infrared telescopes, helping us get a better sense of the shape our universe currently has. COBE's findings changed the way humankind understood and studied the cosmos. The mission was so transformative that in 2006, 2 of COBE's lead scientists, John Mather and George Smoot, were granted the Nobel Prize in Physics. COBE itself never returned to Earth. Even now, the spacecraft remains in orbit, decommissioned yet forever adrift, carrying the echoes of the universe's first light. Dr. Michael Hauser, one of the mission's key scientists, reflected, quote, the COBE mission is worth every ounce of effort we put into it. Cosmology is a very difficult problem to study. We are given very few fossils on the beach. Those few that are still present and accessible are worth every bit of scrutiny we can give to them. The CMB was one of those fossils, a rare and precious clue to the origins of everything we see and know today, which Kobe helped uncover.